If you've ever taken 3 attempts to plug a USB in, click the subscribe button. What's up everyone, my name is Mike and welcome to the Premier Aerodynamics podcast. Today we're talking about cactus-inspired aerodynamics. That's right, there's a cactus out there that has some pretty cool aerodynamics going on, and that's what we're looking at today. The name of the cactus is the Giant Saguaro Cactus. I'm not sure if I'm saying it right, but well, I might be butchering it. And it's the quintessential cactus you see in all the Hollywood movies, where it's the trunk in the middle and those limbs coming up sort of like a person. And the paper that details this aerodynamic feature is called The Mitigation of Vortex-Induced Vibration of Cylinders Using Cactus-Shaped Cross-Sections in Subcritical Flow. And we'll be looking at that a little bit later. So to give you an idea of what this flow control device is, it's supposed to be transferable to cylinders because the cactus itself is sort of like cylinders all stacked upon each other. I've had a lot of cactuses in my lifetime, but never the Giant Saguaro one. I've never actually seen one in real life either. And one of my major life goals is to see one day. So I'm dreaming big. Anyway, so I'll give you a bit of a picture of what this cactus looks like. Let me get the paper up here. Okay, so the paper here, as you can see, and then on figure 1, this is what they look like. So it's the quintessential cactus you see in movies. And it's quite girthy. You can see the guy in there could even fit inside the cactus and you wouldn't even know it. But yeah, they grow to about 11 meters tall, so 35 foot big. I've seen bigger. Anyway, so the flow control device that this cactus has is these bumps around the outside. So this is a cross-section cut of the cactus near its root, just near the base in the soil. And it looks like a regular cylinder, except it has all these bumps along the outside. And these bumps form ridges all the way up the cactus. And what got these researchers' attention to begin with was that this cactus is so big, but it has such a shallow root system. And they thought that, well, if the root system is so shallow, it's not going to have a lot of stability when very strong winds come up. And this is found in deserts, these cacti. So there's going to be very strong winds coming all the time, and they still stay upright. So they investigated these ribs to see what they do to the flow. So to give you an idea of cylinder flow to begin with, let's say this pen here, a regular big pen, is a cylinder. It's approximately a cylinder. It has some edges, but let's say it's completely circular for now. And I'm pretty sure most of you know that when the flow hits a cylinder, and the cylinder acts like a bluff body, so you get this von Karman street typically forming, which is just effectively the flow goes around on one side, it will separate and then roll up into a vortex, and then the flow on the other side will roll up into a vortex periodically, and it would fluctuate in this pattern, one side, then the other side, then one side, and back and forth. And what that roll-up does is create this force. So anytime that the flow separates, there's this imbalance in the force on the cylinder, and it'll move from one side to the other and back and forward, and that creates something called a vortex-induced vibration, or VIV for short. And we actually have a good flow control device that can get rid of VIV. It's been around for like 50 years, maybe longer, and it does a really good job. It's called a Helical Strike. And you can see them even like if you go for a walk in maybe an industrial area of your city, you might see some chimneys or some smokestacks or whatever. And sometimes you'll see these coils on the outside of them, and they're helical strikes. So if you've never seen one of these, just imagine thinking of a screw, like a regular screw into wood, and that helical section on the outside, that's effectively a strake. It's just got a very small pitch, so there are lots of loops going around. Most of the time, strakes, there might be 2 or 3 loops going up the entire cylinder. And I'll show you a picture of what they look like. So this is just a typical picture of 2 cylinders. For those of you listening at home, it's they're just 2 cylinders with this wire effectively going around the outside, a few loops from the bottom to the top. And helical strikes are quite effective. They can cut out like up to 99% of the vortex-induced vibration, so that's very effective. This flow control device, however, it acts in a slightly different way to how helical strikes work. And we'll get into that in a little while. But first, let's talk about how helical strikes work. So as I mentioned, it's the coil around the outside. And if you don't have a coil, what happens is the flow hits the pen or the cylinder, the pen's the example that I'm using, and it will start to separate on one side. Now, that's not necessarily a bad thing, but when it becomes a bad thing is that the flow separates at the exact same time at the exact same location. Now, what that results in is all this force being produced in the same region, in the same direction, and that's going to summate and push the cylinder to one side, creating a force. And that start of the vibration, because for vibration you need to go back and forth. But then when the flow separates on the other side, then the resulting force pushes it to the other side, and that's when you get the full vibration effect happening. So this is effectively what's called a coherent separation, when all the flow on one side separates at the same time in the same location. It's called coherent. That's a fairly important term in aerodynamics, and you can use it in other situations as well when things happen together in the same sort of setting. Now, helical strikes, on the other hand, they break up this coherent shedding. So what they do is, with that screw-like feature around, they let me get that picture up once again quickly. So with this coil around, you're no longer going to be getting separation at the exact same location along the side of the cylinder. So you might get some flow separating a little bit towards the front of the cylinder. You might have some separating around the back to the side. So the force is no longer in the exact same direction, the vector, when you summate it. It's in all different directions. And on one side, it could separate sooner than on the other side. So you don't actually get all the force in the same general direction. It can cancel out. And that's what makes helical strikes so effective. Now, these ribs on this cactus, they're very different. And I'll get into how they've looked into this. So that in this paper, they had a really good research approach. So they used CFD with experiments really well. Like when you use CFD with experiments, often it's really easy to think, oh, I need to make my CFD so good, really high fidelity, so then it can sort of shed so much light onto what's going on, and then your experiments might come in and show some other things. That's great, except often it's so computationally expensive. It takes so much time and so much CPU power just to do a CFD simulation that you can't do so many of them. What these people did was they wanted to use CFD to look at all the different parameters. So with these ribs, you can either have lots of these ribs spaced around the cylinder, or you can have just a few, or you can have very small ones, so the amplitude isn't very large, or very large amplitude ones. And they wanted to figure out, well, which ones are going to be better. And so they used CFD as a preliminary analysis to figure that out. And what they did was they looked at 2D CFD. So they just took one cross section, put it into the plane, and then ran the CFD on that. And to set it up, they did all the usual stuff like mesh independence study, y plus below 1. They used for the turbulence modeling, they used RANS, so turbulence modeling, they used the SST K omega. And that's actually quite good. Like they could have gone with like K epsilon or whatever, but even SST, but SST K omega is very good in this situation because one, it's very laminar. So the title of the paper I mentioned before was in subcritical flow. So subcritical flow is when the flow is laminar. It hasn't transitioned to turbulent yet. Now, using other RANS turbulence modeling like K omega or even K epsilon and SST, they're usually not good at the best of times. So using SST K omega, that is actually quite decent. And they ran these simulations on like quite a few different geometries. I'll go into them shortly. And if we look into figure 5, which is where the juicy stuff starts to happen, I'll get down to figure 5 here. So that was just the mesh up there, a typical mesh. Anyone who's just listening to this, typical mesh that you see where it's very refined upstream, downstream, and to the sides, and then you have the boundary layer mesh happening here. So nothing too out of the ordinary. The figure 5 is the where they calculated the lift coefficient, the drag coefficient, and the Strouhal number of these cylinders with the different cacti ribs on them. So in each one of these figures, they have a straight line, straight solid black line here for the smooth cylinder, and then the different symbols there for the different cactus ribs. Now, as drag coefficient Strouhal numbers referred to, with the lift coefficient, that's effectively the vortex-induced vibration component of the flow, because the lift is always acting perpendicular to the oncoming stream, and that's what's producing that force for the vibration. The drag coefficient is just the bending back of the cylinder, so it's acting in the same direction as the free stream flow. And the Strouhal number, if you're not familiar with the Strouhal number, it's effectively just a way of non-dimensionalizing the frequency shedding or the frequency of whatever's happening. So in this particular case, it's the flow coming around the cylinder and separating. Now, the different configurations that they used for the cactus ribs, they had N, which was the number of ribs going around. And when you have 8, they all spaced around equidistantly. So when you have 8, they're still completing the entire circle around the cylinder. It's just that they're spaced further apart, and so the pitch is greater. And then went up to 24, so 3 times the amount. So the pitch became very small. And then they tested a few in between. And then they also looked at the different diameters, the different amplitudes of the ribs, and they referenced it to the diameter of the cylinder. So they went anywhere from 2% of the diameter in the amplitude to 8%. So that meant that for the biggest diameter, for the biggest amplitudes, the entire cylinder with these ribs around there was actually 16% greater diameter than just a smooth cylinder. And that's something that's important to note, because the characteristic lengths that they used in these figures to non-dimensionalize the parameters to get to this coefficient, the drag coefficient, and the Strouhal number, they used the reference length for the smooth cylinder, regardless of whether it was a smooth cylinder or the one with the cactus flow control device. Now, I'm not too sure why they did it. They said so they could compare more directly, but we'll get into that in a second. What you can notice here is that in figure 5a, pretty much any appearance of these flow control devices dramatically reduced lift. Now, there are a couple configurations that didn't, but by and large, they all did, and by a lot. Like when you look at when they had 16 or even 20, 24 of these ribs going around, the lift coefficient dropped it by like half. So it dramatically reduced the VIF. Now, the drag coefficient, they all increased slightly. And the characteristic length sort of plays a role in this, but it is also due to the difference in the flow physics. So there was definitely an increase in the drag coefficient for all of these configurations. And then when you have the Strouhal number, now this is where things get a little bit interesting, and that's what I was talking about earlier with the characteristic length. So the characteristic length is involved in the Strouhal number. You calculate it by the frequency of whatever's happening. So in this case, the vortex shedding times by the characteristic length divided by the velocity, the free stream velocity. And in this particular case, they use the characteristic length of the smooth cylinder to non-dimensionalize all of these cylinders, regardless of whether it was smooth or it had these cactus bumps. Now, the good thing is that regardless of the cactus bumps, this Strouhal number dropped significantly, which means that there was some effect on the flow physics. It means that it reduced the frequency to some extent of this shedding. However, if you factor in the characteristic length to change, for example, with the h equals 0.08d, which means that the amplitude of each bump was 8% of the diameter, that means that the diameter of this cylinder is actually 16% greater than the smooth cylinder. And if you factor that into the Strouhal number, it takes up a lot of that difference. So not all of the difference that you can see here is just due to the change in flow physics. It's also due to the diameter, change in diameter of these different cylinders, these cactified cylinders. And they actually went into quite good detail. So they looked at the flow physics happening on these cacti cylinders, whatever you want to call them. And it's really cool because they plotted the vorticity in the wake of the circular cylinder with the smooth outside and the cactus cylinder. And in this figure here, they only showed one particular configuration as a representation. And immediately you can see that, typically speaking, the maximum vorticity in all these vortices that are shed are lower than the smooth cylinder. So that means that the cactus cylinder is making these vortices not, well, I'll get into that in a second, but they're reducing the vorticity. Now, you might say that they're reducing the strength of the vortex. That's not necessarily true. To determine that, you need to determine what the circulation is around each one of these vortex centers, or each one of these vorticity centers. And once you figure out the circulation, you can figure out whether the strength is lower or higher. Now, having said that, the maximum vorticity is lower, and they're about the same size as this vorticity range on each side. So there is a very good chance that the circulation is lower. So it would be feasible that the circulation is lower and the vortices are weaker when you put these ribs on the outside. Now, another interesting thing to note, which we can look at definitively, is how many of these vortices there are. So if we were to just count how many vortices there are in the downstream, you'll see that there's a lot more for the smooth cylinder than the cactus cylinder. And that means that the frequency of the vortex shedding is greater for the smooth cylinder. Otherwise, there'll be not as many. So that does agree with the straw number that we saw earlier. And to me, the best figure in this whole thing is figure 7. So what they looked at here was the boundary layer profile, effectively. They looked at the velocity very close to the surface and for the cacti to see what was going on. And what they found was that in the troughs of these cacti, so between two peaks of these ribs, there was this recirculation zone, and then the flow, like sort of the rest of the flow sort of skips over it and makes this separate little recirculation zone very close to the surface between the two peaks, and then it's sort of segregated. So that was really interesting. So we get an idea of what's going on here, because between these two figures, you can see that these cactus ribs don't actually act the same way as helical strakes. With helical strakes, particularly in figure 6, you'd see a lot less coherent motion here. So you wouldn't see these very distinct vorticity centers, these local maxima occurring, and likely meaning that the vortices. You would see more just like just a mix of just random stuff all just thrown in together, just a general wake, because that's what helical strakes are supposed to do. They're supposed to break up these vortices from being able to form through not being able to have coherent shedding and getting rid of that. Now, after this, they've looked at the CFD and they saw what was going on. So they picked a few different cylinders with these ribs, and then they put them into a water channel. Before we get to that, I just want to talk about this podcast is brought to you by the Atmosphere Hawk. So I brought this up last podcast. What this does is it accurately measures the temperature, barometric pressure, and humidity in your experiments. And the reason why you need to do that is because on any given day, these parameters are going to change enough so that the density of air is going to change around 3 to 4%. And if you don't measure these parameters, the density of air, this error, is going to creep through in all of your measurements. So the Reynolds is going to get affected, this Elliptic coefficient, drag coefficient, all your measurements are going to get affected. So if you don't measure these parameters, you got like a 3 to 4% error in certain measurements for no reason, including the velocity of your free stream. So make sure to pick one of these up. It's very easy to use. You just plug it into your computer via USB, and it does it for you. It's very accurate. Okay, so back to the podcast. Now, with the experimental setup, they I'll go to these figures here. They sort of just show you they had these cylinders and they put them into the water, and they had strain gauges on it to determine what the strain was when the cylinder was flexing. And from there, they could calculate the forces. And they also had this really cool way of making these cylinders. So they had the smooth cylinder, and they could put different sleeves on the smooth cylinder to put these different cacti ribs on. And here's just some examples of what they were doing. So these cacti rib sleeves were able to go over the inner smooth cylinder to then give whatever configuration they wanted. Then from there, they tested it and they looked at the VIV response, so the vortex-induced vibration response of a particular cactus-shaped cylinder. And in this case, it's one called R800.04. Now, what this means is that they had 8 of these ribs around the cylinder, and these ribs had an amplitude of 4% of the diameter. Now, in this plot, this has a lot of juicy information here. On the y-axis, it has the RMS of the microstrains. And what this means is that obviously when you have a cylinder and it has some VIV, it's moving back and forth. So this elliptic coefficient is fluctuating. It goes from positive to negative, and so on. So take the RMS of that, you actually get an idea of how much lift there is on this cylinder at a given time, or the maximum. Whether it's positive or negative is sort of beside the point for VIV because it fluctuates between the two anyway. Now in this, and then on the x-axis, they have what's called the reduced velocity. Now the reduced velocity is effectively, it's akin to the Strahl number. It's just a way of non-dimensionalizing the velocity so that you can compare 2 different cylinders at 2 different velocities and still get an idea of what's going on. You can compare them. And the IL means inline microstrain. The CF means cross-flow strain. So the CF is what creates the vortex-induced vibration. The IL is just the bending back of the cylinder, so the drag. And they have the circular, the smooth cylinder, which is in black and red, and triangles and asterisks. Sorry, in black, so the triangles and squares. And then they have the cactus one, which was in the blue and in the red. Now, the IL, the inline force, that's quite interesting to look at. Just if we look at this one first, you can see that as the reduced velocity increases up to a certain point, the drag increases accordingly. Now, remember, the inline force is effectively just the drag. And the cactus ribs, they actually reduce the drag dramatically. So you can see at some points it's like, I don't know, like 3% of what the circular cylinder was experiencing. So that cuts out the drag dramatically. That's really amazing. Then if you look at the cross flow, this is where things get even more interesting. So the smooth cylinder, you see it increases as the velocity increases, and then it gets to sort of this plateau range and then drops dramatically. I want to talk about this curve first because this is quite interesting. It shows this is applicable to pretty much all cylinders. And this plateau here between a reduced velocity of about 4.5 to about 10, this is what's called the lock-in range. Now what the lock-in range is when the frequency of the vortices that are being shed is very close to the resonance frequency of the cylinder. Now you might say, well, this is over quite a wide reduced velocity range. So why is there such, it's not going to be the resonance frequency, that's only going to happen at one particular point, but it's only going to be at one reduced velocity. Well, that's where lock-in comes into effect. Once the resonance frequency is sort of close to what this frequency shedding is of the vortices, it's very difficult to actually break out of that resonance frequency. So it locks in. So you either need to really increase the velocity or really reduce the velocity to break out of that. And that's why you see it when you go to a reduced velocity of 11, you get this dramatic drop in the cross-flow strain, the VIV effectively, because you're now breaking out of that lock-in. If it wasn't for that lock-in, there would be a much more gradual decline from earlier on because you're not near the resonance frequency. And this is where the cactus ribs are really effective. So they dramatically reduce this plateau. So you're only getting this lock-in range for a much shorter time periods, much shorter periods. So only from about a reduced velocity of 4.5 to about 7.5. So that's so not only is the cross-flow force less, so the vortex-induced vibration is less, there's a smaller lock-in range, which means that you're not getting as much force later on at a higher velocity. So that's all good. Now, after this, they also plotted in figure 13 the microstrain as a function of time for these two cylinders as well. And this is just to confirm what you already know, which is it fluctuates dramatically. So for the inline force, you can see that even that fluctuates a little bit. So for the circular cylinder, the smooth one, it goes from about 150 to about 250 microstrains. And the cactus ribs dramatically not only drops that, but also the amplitude of that oscillation drops as well. Now with the cross flow, two things that are interesting happen. One, you obviously get the oscillation happening. So the microstrain for the smooth cylinder goes from -200 to 200, which is to be expected because you have the this periodic fluctuation in the perpendicular force. And the cactus cylinder dramatically reduces that. So instead of having an overall amplitude from like the absolute change of -200 to 200, so 400 microstrain range, it's now only from about -50 to about 150 or so. That's only 200 microstrain range. The interesting thing is, though, instead of being centered around zero, it means that the force is consistently on one side more. So you're going to be producing force overall on one side a bit more, so it's going to be leaning a little bit. And why that is, I'm not too sure. I have a feeling that it might be that when you put these ribs around the cylinder, if you don't put the cylinder in a flow such that the flow hits it at a point where the two first amplitudes are directly the same distance away from the stagnation point, and so in other words, it's skewed a little bit, it's off center, then the flow is going to separate on one side a bit earlier than the other. And I think that's what might cause this this asymmetry here, but I'm not too sure. They didn't go into that. Now, after this experiment, they then looked into what's called tandem cylinders. So in tandem cylinders, you have, it's exactly what it sounds like. So you have one upstream, one downstream, and the flow from hits the first one, it sheds, creates a wake, and then that wake will typically interact with the one downstream. And interesting thing to note is that the downstream cylinder, it won't experience what's called viv, it could experience something called wiv. It sounds the same, but it's, it's a kind of play on words. So the upstream cylinder will experience vortex-induced vibration. The downstream cylinder will experience wake-induced vibration. And it's just a significant difference in how the flow physics plays out. And the reason why this is important is because we haven't actually, as far as I know, we haven't cracked how to mitigate wiv. So even if you put helical strikes on the upstream one, the weight coming off of this will still impact the downstream and create this wiv. So it's still going to be vibrating around. And helical strikes, regardless of whether you put it on both, just one or the other, it won't be able to mitigate that. So they wanted to test whether these cactus bumps will mitigate this. And they put these two cylinders at different distances away from each other. So they started off with, I think it was 4 diameters downstream, then 5, and I think they went all the way to 8 diameters, I think. And in these figures, this is figure 14, I think it was. Yeah, this is figure 14. They, on the left side, the left column, they have the upstream cylinder. On the right side, they have the downstream cylinder. And one thing to note is the downstream cylinder didn't really have didn't get much benefit from having these ribs along the side, on the outside. Both the inline and the cross flow forces, they weren't really affected. So in effect, the downstream cylinder still experienced the wiv, so wake-induced vibration. So that's not that great, but there was an effect upstream. So if you remember from before, we were looking at just one cylinder by itself, either with a smooth outside or with the cactus bumps. When you put the cactus bumps on there, the lock-in range dramatically drops, if you remember. Well, when you put these two cylinders in tandem, now that sort of mitigates to some extent that reduction. So when it was 4 diameters spacing, these two tandem cylinders, the lock-in range was actually now extended. So it went from about 4.5 to about 9, 10 or so. So that's not a great thing, but it is interesting that the downstream cylinder significantly impacts the upstream cylinder more than what you would think. Now that could be because this is such a low velocity, it's low Reynolds number as well, but I don't know. And then when you move it downstream, it also affects this lock-in range. So you can see at 5 D downstream, now it sort of dives down a little bit, so it only takes place over maybe 4.5 reduced velocity to about 6.5 or so, 7. Then when you go to 6 diameters downstream, you get this really funky graph. So there's a point where there is a massive lock-in range, then it drops down a little bit, and it goes back up a little bit. So what's going on there? I have no idea. I didn't get into that. And then again, as you go further downstream, you get something similar happening where it sort of plateaus out and then goes down and dips down. So that's where they came to the conclusion. So overall, these cactus bumps performed pretty well, like about similar to helical strikes, not as well, but that's probably because they haven't optimized the shape of these ribs, so they could make a much better. Helical strikes have been around, as I said, about 50 years, maybe even longer, and they've gone through so many iterations, and people have really optimized them. The early helical strikes, they still weren't as effective as 99%. They might have been like 60% effective or 50% effective, which is similar to what these are now. So with additional investigations, it is possible that these cactus ribs could perform a lot better than what they are, and maybe even better than helical strikes. The interesting thing to note is how different they are in how they achieve their goal. As I mentioned earlier, the helical strikes, they break up this coherent vortex shedding. The cactus bumps, they have this just very different flow physics altogether. There is still this coherence shedding to some degree, but it reduces the frequency somehow, reduces how much force is imparted onto the cylinder. And what's interesting to note is, as I mentioned before, there is this upstream and downstream effect. So the downstream cylinder affects the upstream flow physics, which isn't that surprising, but the fact that these cacti, if I go back to figure 1, these cacti, they have multiple limbs coming up, like a person with their arms up. No matter what direction the flow is coming in at, it's going to be resulting in one cylinder at least is going to be upstream, the other cylinder downstream. So I wonder if cacti have evolved so that they overall the force is reduced because they have so many different ones around, and they interact in a way that is beneficial to the entire cactus, not just the one cylinder or the other cylinder, one of the limbs of the other limb. And so how would I rate this paper? Well, I'm going to introduce a scale called the Jeff Goldblum scale, and it ranges from 1 Jeff Goldblum to 10 Jeff Goldblums. And obviously 10 Jeff Goldblums is the best. I'm going to rate this paper 8 Jeff Goldblums out of 10 Jeff Goldblums. And I know people are going to be saying, oh, well, why don't you give it 9 Jeff Goldblums? Well, I would, but there's one fact, and that is this was conducted in water, and we all know that air is better. People drown in water. I've never heard of people drowning in air. So for that reason, I'm going to give it 8 Jeff Goldblums. All right, so that's the end of this podcast. Make sure to like and subscribe. Check out the Atmosphere Hawk, link in the description, and peace out, amigos.